Okay. Okay, so so today we are going to discuss two topics on springs. So these are the final topics which are left in springs. So one, springs which are connected in series and connected in parallel. Okay, so let's start with the first one, springs connected in series. Springs connected in series. See, if you see the real applications of springs, so there will be multiple springs, so which might be connected in series. Sometimes they connect even in parallel also. Okay, so when they're connected in such a way, so definitely the stiffness of the springs will definitely vary. So we are supposed to see what will be the consolidated deflection of the whole uh, springs which are connected either in series or in parallel, and how the load going to be distributed. Okay, so let's see the picture. So based on that, we can able to understand so the real applications of springs where they are going to be connected in series. Okay, so let's see this picture. So this picture shows you clearly where the one end of the spring is fixed, okay, and other end which is subjected to a load. So here you have two springs. So the load is going to be common, right? So the load which is acting on the spring will be axial. And what happens here to the load? If you see the inversion here, so the load will pass through the center of the spring axis, isn't it? Okay. So whatever the load acting on the spring, let us consider it as W. The load will be same in the second spring and even in the first spring also, isn't it? So here the load is not divided. Okay, so then what happens to the stiffness of the spring? So the stiffness of the spring will vary, because here the stiffness of the spring is K1 and the stiffness of the spring here is K2. So on what based you are going to define the stiffness over here? So we define stiffness as load P or W. Okay, load per unit displacement, isn't it? So what happens here, displacement, the overall displacement of the spring is delta. Displacement of the first spring plus displacement of the second spring will use the consolidated or the overall deflection of the whole unit, isn't it? Right? So this is what the deflection, right? And what about the stiffness? When the deflection varies, automatically stiffness also will vary, right? So why? Because your stiffness is always depends on deflection. It won't directly depends on the load carrying of the spring. Okay, so by that, here the stiffness of these springs which are connected in series can be written in this form. Okay, so let me show it clearly how it is going to be shown. One second. Okay. Yeah, so let me draw this first one, spring which is connected in series. You can take multiple springs. Okay, first spring, second one, and third one. So there are three springs which are subjected to load W. Okay, so this picture or this figure shows three springs which are connected in series. So here each spring carries the same load W, so which is applied at the end of the unit, right? And the total extension in the sum of these extensions of the springs are going to be calculated in form of a delta. So here delta of the first spring is delta 1, delta of the second spring is delta 2, and deflection of the third spring is delta 3. Okay, so this represents deflection. And what happens to the stiffness? Stiffness of the first spring is K1, stiffness of the second spring is K2, and stiffness of the third spring is K3, right? So K1, K2, K3 are the stiffness of the whole spring components, and K will be the stiffness of the composite springs. Okay, so I can consider K as overall stiffness of the unit, and I can consider delta as overall deflection of the whole unit. Okay, so how can I represent here? Total extension, I mean, or total deflection or total deformation. Okay, you can call in any way. So total extension is equal to what? Sum of extensions of three springs, isn't it? There are three springs. Each spring is having different deflections. So by that, total deflection will be deflection of the first spring plus deflection of second spring plus deflection of third spring. Okay, but we know the formula. Stiffness is represented as load per unit displacement, right? Right? How can you write a deflection here? Deflection can be written as load by stiffness. Okay, so let me write this in this form as load by stiffness is equal to load by stiffness of the first spring plus load by stiffness of the second spring plus load by stiffness of the third spring. Why load is constant? Why? Because load which is acting axial to the whole unit. Okay, by that, load carrying by the first spring will be same to the load carrying by the second spring, and as usual load carried by the third spring also will be same. So by that, W is constant. You can write it as 1 by K is equal to 1 by K1 plus 1 by K2 plus 1 by K3. So this is the stiffness equation or stiffness relation where the springs are connected in series. Okay, so this is what we need to understand it clearly. Understand? Yeah, very important, Amma. So based on this equation, you can able to calculate what is the overall extension of the springs which are connected in series. At the same time, we can able to calculate what is the overall stiffness of the whole unit. Okay, so because each individual springs have its own spring constant here we calling it as modulus of rigidity. Okay, at the same time each spring is having its own stiffness value based on its deformation or based on its deflection. Okay, so by this you can able to calculate overall stiffness and overall extension of the whole unit. Understand? So this is what about the springs which are connected in series, right? So please try to remember here. Even in your competition exams, they may ask this in three different ways. First one, they may ask you to calculate the total extension, or they may ask you to calculate the overall stiffness of the whole spring unit. And third one, you have to understand which is constant. Here load is constant. Okay, load on each springs is same. Okay, so that you need to make sure. Clear? Right. So now next one we will discuss about springs which are connected in parallel. Okay. ఇది అందరికి అర్థమైందా? Guys, is it clear? You may ask me, sir, when the load is same in all the springs, why deflection varies అని మీరు అడగచ్చు. Okay. So there is a reason. Why? Because if you see the first spring is very near to the support. Okay, so when the spring is near to the support, what happens? The deformation of that spring will be always less compared to the spring which is far from the support. Okay, if you take example, let me write one example clearly where you can able to understand from your shear force and bend moment diagrams. Let us take a cantilever beam, so which is subjected to point load at end. If you see the bend moment diagram of this. What is the bend moment diagram? Isn't it? Is the bend moment diagram? Right. So what happens? The bend moment is maximum at the support and bend moment is zero at the free end. Right. So here, as it is having more resistance, so there will be more bend moment at the support. Okay. So as this is W, so you can have the same reaction at end. Okay. Sorry. W into L at the end. Okay, so always the resistance towards the support will be more compared to the resistance at the free end. Okay, so in that way, even you can able to understand springs also will have different deformations or different deflections, even though where they are connected in series. Okay, right? So that is the reason why near support, the spring will have less deflection compared with the spring which is connected at the free end. Okay, so that's why deflection is varies at all the stages of the whole unit, right? Guys, understood? So shall I move on to next where the springs connected in parallel? Maybe he mean power systems lab. Okay, clear, guys? ఏమా అందరికి అర్థమైందా? Guys, you have to respond. Clear?
Yes, sir.
So now we will discuss next one, which springs which are connected in parallel, right? Springs connected in parallel. Okay, so after this I will give a differentiation which connections, I mean so in which way the springs will have more stiffness. So based on that they will try to choose whether they want to connect the springs either in series or parallel. Okay, it all depends on the stiffness of the members, stiffness of the springs, at the same time even the applications of the particular springs also. Okay, so let me draw how the springs are connected in parallel. So let me take a fixed end. Okay, the first spring which is connected like this, and second spring connected here, and third one is here. Okay, so for the whole unit load is W. Okay, right. So now this is called springs which are connected in parallel. So now tell me what happens to the load. Load will be same in all the springs as like in series? Will the load will be same or not? So when they are connected in parallel, will the load will be same in each spring summer or will it be different?
Same in each spring, sir.
Same in each spring. Huh? See, when the springs are connected in parallel, this load will divided into 3 equal parts as W1, W2 and W3. Might be 3 values of W1, W2, W3 might be same as they are all connected at the same height. Okay, if you take this example, so let me take another example like this, where this spring is connected like this and the other spring is having a different in weight. Okay, okay, so if you want to connect these kind of springs, right, so with the different load, so what happens again, load will be different for the both springs. Okay, so here the load which was divided, I mean the load carrying by each spring will be different, it won't be same. Okay, so the overall load is divided for 3 springs as W1, W2 and W3. So this is how load varies. Then what happens to deflection? Load varies, what happens to deflection?
Deflection also same, sir.
Deflection will be same. Okay, so deflection of the first spring will be delta, deflection of the second spring will be delta, deflection of the third spring will be delta. Why? Because loads are same. Okay, loads are same, but the load carrying by each spring is different. But coming to deflection of this spring is same, deflection of this spring is same, deflection of this spring is same. So that is delta. What happens to the stiffness? what happens to the stiffness?
Stiffness also same, sir.
Stiffness is always depends on the load, isn't it? So
Yes,
stiffness
sir.
K1 of the spring, stiffness K2, and stiffness K3. So here the common parameter which we can write here, the extension of three springs is equal, while the sum of the load carried by each spring is going to be equal to the external load. So that means the external load is W. External load is the summation of W1 plus W2 plus W3. Right? So, but earlier in springs which are connected in series, what we have written? What we have written there? Load is common. You have written delta is equal to delta 1 plus delta L2. So that means summation of deformations will reflects the overall extension, isn't it? But here springs, when they are connected in parallel, here the summation of load will gives the overall load carrying by the whole unit, right? So here what we can write, total extension, total external load will be equal to total external load will be equal to summation of load carried by each spring, right? Summation of load carried by each spring. So that is what we represented here as W1 plus W2 plus W3. Let's write what is your stiffness equation. K is equal to load by delta. Okay. So here what is constant, Amma? You can write load as K into delta, right? Sure? So you can write load as K into delta, right? So now with this relation, you can write your whole equation as W is equal to W1 plus W2 plus W3. So what is W? Delta into K is equal to delta into K1 plus delta into K2 plus delta into K3, isn't it? So finally, which is constant here? Delta is constant. Why? Because all springs are connected at the same height, where they are connected in parallel. So deflection of the first spring will be same to the deflection of second and third spring, right? So by that, finally you can write as K is equal to K1 plus K2 plus K3. Okay. So here we have to understand clearly, when springs are connected in parallel, the overall stiffness will be summation of each spring stiffness, K1 plus K2 plus K3. Okay. But when the springs are connected in parallel, it is inversion of springs. So that means 1 by K is equal to 1 by K1 plus 1 by K2 plus 1 by K3. Okay. So that is what we have to be clear when the springs are connected in parallel. Okay. And one more thing. So here three important points you have to remember. One is the overall load will be equal to summation of load carried by each spring. So that is one point. The second one is deflection will be constant in each spring. So that means same will be same in the each spring. And third one, overall stiffness of the unit will be equal to summation of each individual spring stiffness values. Okay. So that's what we need to understand from this concept. Clear? So let me show you in real application. So where it will be like this. Kanpistunda? Clear? So these are the two important points, Amma. I mean, even very important for solving problems also, right? So because in the previous topics, so we have discussed how the deflection formula can be written for open coiled helical spring and closed coiled helical spring at the same time. So what is deflection of leaf spring as well. Okay, so if you see the deflection formula for closed coil helical spring, the deflection of the closed coil helical spring you have written like this. What is that? Can anyone? What is the formula of deflection for a closed coil helical spring? Which is delta is equal to 64 W R cube into N by N d power 4. So this is the delta formula of each spring. So but now when the spring was connected in series and parallel, here deflection will be summation of delta 1 plus delta 2, but here deflection will be same. Okay, so that you need to understand it clearly, right? Okay, clear? అందరికి అర్థమైందా? ఏమా క్లియర్ ఉందా? Two concepts, springs which are connected in series and springs which are connected in parallel.
Yes, sir.
Right, now I request all of you, so please note down this, very important. One second, let me erase this, so by this you can note down it in your running notes. These are very important. So this table will use a clear differentiation between springs which are connected in parallel and series. Okay, so let's see the first one. First one, equivalent spring constant. Okay, what is the equivalent spring constant in series and parallel? Here K is equal to K1 plus K2. Just now what we derived for springs which are connected in parallel. What happens in series? 1 by K is equal to 1 by K1 plus 1 by K2. So that we are calling it as an equivalent spring constant. So please note down this amount. So this table will use a clear differentiation between these two, and it is going to be useful for your competitive exams also. Okay, so to remember the formulas easily, and you can be able to differentiate them easily. Second one, equivalent compliance. Okay, equivalence compliance. What do you mean equivalence compliance? What is this? Equivalence compliance, and K is the stiffness constant under the. Okay, so what is this? Can anyone?
Shear modulus.
Very good. Shear modulus of two different springs. And third one, strain elongation, which reflects the deflection delta. So in the springs which are connected in parallel, your deflection will be same. By that, equivalent deflection will be equal to deflection of the first spring and equal to deflection of the second spring. But in series, overall deflection will be equal to summation of first and second spring, right? So that is what about strain. And fourth one is stress, force applied, so which reflects here as force carried by each spring or load carried by each spring. Equivalent stress applied is equal to F1 plus F2 in parallel, but in series equivalent force is equal to same force carried by each spring. F1 is equal to F2. Okay, and the last one is strain energy. What do you mean strain energy? Energy stored in a body to regain its original shape and size. So that is what is stored energy. So here stored energy also you can write it like this. Stored energy, equivalent stored energy is equal to E1 plus E2. Even in series, equivalent strain energy or stored energy is equal to E1 plus E2. So there is no difference where the springs are connected in parallel in series. Why? Because if you see the springs clearly, guys, see here the strain energy stored in a body or a strain energy stored in the first spring will be same where the strain energy stored in the second spring. Okay, so the total strain energy we can able to get only by summating these two strain energies carried by each spring, isn't it? Even in parallel also it was same. If you want to calculate the equivalent strain energy of the overall unit, so you have to add strain energies carried by each springs. So then only you can able to get the overall strain energy. So that's why if you see the difference of quantity in terms of stored energy in parallel and series, both are same. Okay, right? So here you can find the difference. Rest of all you can able to understand it clearly because we have just seen them in the derivation, right? So but stored energy matram parallel lo series lo rendu same untundi. Okay, so please try to understand it and you can make use when they ask you, I mean when they ask you to calculate stored energy. So stored energy in parallel and stored energy in series will be always same. Okay, so you should not differentiate these two in a different ways, right? Okay, note chesar andaru. So then I can show you the real applications of springs which are connected in series and parallel. Fine, note chesara idi. Yes, ఏమన్నా నోట్ చేశారా? సో లెట్ మీ షో యూ. చెప్పండి అమ్మా. నోట్ చేశారా?
Yes, sir.
Okay, right. So let me show you straight away real applications. Real-time applications. See, there are a lot of pictures, but see, majorly they use springs like exclusively this what we call open coiled helical spring, because the springs which we are discussing right now, they are all open coiled helical spring. So why? Because you can find deflection, okay, only in majorly in open coiled helical spring than the closed coiled helical spring. So why? Because you can't see much deflection in a closed coil helical spring. Why? Because there won't be any fixed distance in between two coils. Okay, so this happens in only in open coil helical spring, and the two open coil helical springs are majorly subjected to what? Tension. Okay, so they use these springs only where you need spring should carry the load at the same time where the springs are subjected to tension. Why? Because closed coil helical spring will be only used to carry the compression forces. Okay, so that's the reason why even in derivation example which I have showed, where the springs are subjected to tension, isn't it? So where you can able to calculate the deflection and you can able to see the load carried by each spring clearly, right? So if you see the applications, real-time applications, I can't find many. If you see in a suspension of axle, okay, even in the suspension of axle, if you want to distribute the load not just to the single spring to the multiple springs, then you can able to connect the two springs in parallel. Okay, so here you may ask me, sir, which is always preferable to have the effectiveness of the connection? So where the springs are connected in series preferable, springs which are connected in parallel preferable. Okay, so if you see the relation, just I will show you both in a single picture. Okay, see. So when springs are connected in series, so what is your stiffness summa? 1 by k is equal to 1 by k1 plus 1 by k2, right? In parallel, what happens? K is equal to K1 plus K2. So here the overall stiffness is giving the maximum carrying capacity, or you can call stiffness of each springs. But here the springs is the stiffness of the springs are the reciprocating the thing, right? Isn't it? Right? So if you want to choose for your application, which you will choose preferably to have more stiffness of the connection, ఏది చూస్ చేస్తారు మీరు రెండిట్లో? Will you choose springs are connected in parallel or series?
Parallel.
Why parallel? Because you can have more stiffness, which gives the summation of two individual stiffnesses. But here, when you will prefer this series, when you will prefer the springs which are connected in series, when you will prefer, for which kind of applications you will prefer springs connected in series?
Where more load is not applied or deflection
Yeah,
will be less.
exactly. So where the more load of the, I mean, the whole unit doesn't carry any load. Okay, if you see here, your deflection will be the summation of delta 1 plus delta 2, right? Here the deflection is going to be carried by each member, where the deflection will be more. Okay, here stiffness is more, but in series deflection will be more. But what happens to deflection in parallel? Deflection is same, right? But here deflection is more, here stiffness is more. So we always prefer to try to make your connection in parallel to have more carrying capacities of the spring, to carry more tensile forces in the spring. Okay, so if any application, if you want to see the more deflection, especially in the springs, you can go with springs which are connected in series. Okay, so this is what we have to understand, where we can use series and parallel, okay, of springs connections, right? Okay, so what happens in the first unit, I will try to cover a few problems on springs. So by that we can move to curved beams, right? So by that we can finish the first unit. So we can start immediately the third unit, Amma, so which is very unique. It doesn't have any prerequisite. So by that we will start thin cylinders and thick cylinders, so where you can finish in you know bit early. So by that we can have second unit of, which is a mid half for the first mid examination. Okay, so all of you, so please go through all the formulas. We will have class tomorrow, where we will try to solve 3-4 problems on springs. So on each model we will do one problem on series, one problem on parallel, one problem on closed coil helical spring. I think we have solved one problem on closed coil. We will do it on open coil helical spring, and one more problem on leaf springs. Okay, so by that we can finish springs. Okay, so we'll start curved beams immediately. Okay, curved beams is very small topic, where you are going to know what exactly the curved beam, where they're going to use, and they are also the same. What is the deflections of the curved beams in both x and y directions? Okay, so that's how we can finish first module by the end of this week, right? Okay, guys. Okay, and I will try to upload this, so you can just verify it again. Okay, ma. So any doubts in today's lecture? Guys, fine? Clear?
Sir,
Yeah, చెప్పండి.
sir, the series which are connected in parallel and series అని
Series.
చెప్పారు సార్ స్ప్రింగ్స్. సార్ అది ఓపెన్ కాల్డ్ సార్ టోటల్?
Yeah, all are open coiled, amma. Why open coiled? Because their springs are subjected to tension. You can't connect any closed coil helical spring which are under compression. All are open coiled helical springs, and all open coiled helical springs will be used only where members are subjected to tension. Okay. Okay, Namma?
Okay, sir.
Right. Anything else? Any doubts? Okay, then we'll meet tomorrow. Okay, we will try to solve problems on springs. Okay, see you. Bye.